Hello and welcome back to another lecture. Let's dig in. You may hear some people like mowing their lawn or something in the background. I apologize for the background noise. One of these days I'll have my own little like sound booth, like recording, setup that'll be really nice. Anyway, but until that day, this is lecture 1.3. And so by now you know the drill, I think, but just in case, you need to make sure that you have the notes downloaded and ready to go, or printed. Downloaded if you are going to use a tablet to write on them, but printed if you're gonna, work with them by hand. And then you also should have the data set downloaded so that it's ready to go, so that you can copy and paste the data from the spreadsheet. From the spreadsheet directly into Art of Stat. So make sure to click on Enable Editing so that you're able to do that. And then I think if you have those things set up, you might also want to have Art of Stat open. So go to artofstat.com, click on Web Apps, and today we're going to be using the Explore Quantitative Data app. So we'll be using that. And then maybe one last thing that you might want to have open is the Desmos calculator. In case you need to do any number crunching, go to desmos.com and then click on Scientific Calculator. Anyway, so once you have all the tools set up, then you're ready to dig in. So let's go ahead and do that. We're going to talk about visualizing numerical data. In the previous section, we talked about visualizing categorical data. But here we're going to talk about visualizing numerical data, and we're going to use histograms to do this. So let's just start off practicing reading histograms a little bit. These are very similar to bar charts. You'll notice right off the bat that they don't have gaps between the bars. So unlike a bar chart, which must have gaps, histograms do not have gaps, and when you're drawing them, you should not include any gaps in your bar charts. But the other thing about histograms that's a little tricky, I think, is that it's pretty easy to confuse the numbers and the counts, right? Because the variable that we're working with is a numerical variable, right? And so it's easy to compare the variable, right, the counts of the variable on the x-axis, the values of the variable on the x-axis with the counts of the variable on the y-axis. So this makes things a little bit tricky with histograms. But so that's kind of the name of the game, is just to keep the counts and the categories kind of firmly separated in our minds. Let's practice doing that a little bit. So number 1 here says the histogram below shows the number of Atlantic hurricanes over a period of many years. And part A asks how many years saw 12 hurricanes, 16 hurricanes, etc. So I will let you pause the video and go ahead and give all of these parts a try, and then I'll check back in with you and give you my answers. So here are my answers. How many years saw 12 hurricanes? Well, to figure that out, we would go over on the x-axis to 12, right? And then we would look at the bar corresponding to 12 hurricanes, and we can see that that there were 5 years, right, where there were 12 hurricanes. So for 12 hurricanes, there were 5 years. Okay. For 16 hurricanes, well, it looks like there were 0, right? There were no years where there were 16 hurricanes, right? So another way to say this is that however many years we were tracking hurricanes, it says over a period of many years, right? But let's just say it was for 100 years. They were tracking the number of hurricanes or something like that. In that 100-year time span, there were no years where 16 hurricanes occurred, and there were 5 years where 12 hurricanes occurred. Anyway, so that's part A. Part B, what was the smallest number of hurricanes in a year during this period? Smallest number of hurricanes in this period. Well, that would be, it looks like 4. It looks like 4 was the smallest number of hurricanes in a year. So we would say 4. 4 hurricanes. Okay. What number, part C, what number of hurricanes per year occurred most frequently? Well, here we would look for the category on the x-axis that has the largest bar, right? The bar that repeated the most, right? And it looks like that would be 11. There were 11 hurricanes in 10 of the recorded years, right? We saw 11 hurricanes, and that was more than any other number of hurricanes, right? 8 is a close second, right, with 9 years that saw 8 hurricanes. But the number of hurricanes that occurred most frequently was 10. And then part D, how many years were the hurricanes counted? So we're being asked for the total number of years in this in this study. Okay, well, if the problem says so, then our work is done for us, but it doesn't look like the problem says. So I think our next best thing is to just count up the frequencies. In other words, there was 1 year where 4 hurricanes occurred, 1 year where 5 hurricanes occurred. There were 6 years where 6 hurricanes occurred, and 6 years where 7 hurricanes occurred, and so forth. So if we add up all of these frequencies, 6, 10, 5, 5, 3, and then 0, 1, 1, right? If we add up all of those frequencies, then we will get the total number of years. I said 100. That was obviously a huge overestimate now that I'm looking at those numbers a little more closely. But yeah, if we add up all those frequencies, then we get the total number of years. So let's crunch those numbers real quick. This is where our little calculator will come into play, but we can do 1 plus 1 plus 6 plus 6 plus 9 plus 4, 6, 10, 5, 5, 3, 1, 1. So it looks like 58, unless I made a mistake somewhere. I'm double checking. Looks good. I think that's right. I think it's 58. Okay. So it looks like they were counting hurricanes for 58 years in this study. Okay. Very good. Here's another example. This one says, the histogram below shows the lengths of a sample of several fish from Black Lake. One thing that you'll notice right off the bat is that on the x-axis, we no longer have one value for each bar. In other words, this bar does not represent 22 or something like that. It represents all of the fish that are between 20 and 25 centimeters long. And this bar represents all of the fish that are between 25 and 30 centimeters long, right? And so forth. So histograms sometimes will look like this, especially if there are a lot of different values. We'll talk about that in more detail in the future, in this section. But let's see what kinds of questions were asked. Part A says, how many fish were between 30 and 35 centimeters? So 30 and 35 centimeters. Okay, so that's this bar right here, 30 to 35. And it looks like there were 5 of those fish, right? So the answer to part A, how many fish were between 30 and 35 centimeters? We would say 5 fish. Part B asks, what proportion of fish were between 30 and 35 centimeters? In order to answer that question, we would need to take the number of fish that were between 30 and 35 centimeters and divide it by the total number of fish in the sample. And again, we're not told. Dang it. I wish they would just tell us there were 60 fish or something in this sample, but they just tell us there were several. So our only option for being able to answer part B is to once again find the total number of fish in the sample, and then we can divide 5 by that total. So there's 1 fish here and 4 there, 5, 6, 7. That was the worst 6 I've ever seen in my life. I've never seen a 6. Okay, 5, 5, 3, 3, and 1. Okay, so if we add all those up, then we can get the total number of fish. So let's see. 40 fish. Okay. And there were 5 fish between 30 and 35 centimeters. So the proportion of fish between 30 and 35 centimeters would be 5 out of 40. Okay, so about 12.5%. Okay. So the proportion P hat is 5 out of 40, which is 0.125. Okay, go ahead and pause the video and see if you can work out parts C and D. I'm going to give you my solutions here. So part C, what length category had the greatest number of fish in it? Again, we're looking for the largest bar. I think that would be this one right here. So the length category would be 40 to 45 centimeters, it looks like. There were 7 fish in that length category. And then part D, how long was the largest fish in the sample? Well, we don't really know for sure. That fish would be in this category, somewhere between 65 and 70 inches, but we don't know exactly what it was, right? So we'll just say somewhere between 65 and 70? Yeah, somewhere between 65 and 70 centimeters. Very good. So as we just saw, sometimes the bars in our histograms don't represent just a single value. Sometimes they represent an entire range of values. And so let's talk about that a little bit more. Okay, we call those ranges classes, right? So oftentimes there's so many values that a numerical value can take on that having each value be its own category in our frequency table or histogram would lead to a pretty useless summary. For example, let's say that this was our data set right here. And let's say that we made each of these values its own kind of unique class. Then the histogram that we would end up with would look like this, which is not super nice. It doesn't give us a ton of really useful information. Similarly, right, our frequency distribution would look like this. And all that's telling us is that all of these weights occur once, or maybe a couple of them occur twice, right? But it doesn't really give us a good sense for kind of the weight distribution as much as we would like. So tables and graphs like these ones, they're just not very useful. And so if the variable takes on a lot of different values, then we'll group the data into intervals called classes. So here's that same data set, but we've grouped the data into classes, right? So our first class goes from 2 to just under 2.5, and then the next one goes from 2.5 to just under 3, and then the next one goes from 3 to just under 3.5, and so forth. And you can see you get a much better kind of understanding of what the weights of babies, how the weights of babies behave, right? Like it's much more common, for example, for a baby to be between 3 and 3.5 kilograms than it is for it to be between 2 and 2.5 kilograms. So, okay. We've already pointed this out, but you'll note that the data in example 2, that was the fish example, this bad boy right here, these were grouped into classes, right? The data here were grouped into classes, whereas the data in example 1 were not grouped into classes. Here, each individual observation was its own class, right? Its own category. That's okay to do as long as there aren't like so many different values that you end up with a nasty looking histogram like this. Okay. The class width, so when we're talking about classes, we'll have a class width, right? So the class width is the width of each bar in the histogram. So looking at this histogram, the width of this bar is 0.5, right? Because 2 plus 0.5 is 2.5, right? So the width here is 0.5. And the width here also 0.5, right? Generally speaking, when we make histograms, we want the class widths to all be the same. If you're looking at a frequency table, you have to be a little bit careful, okay? Because we calculate the class width from a frequency table like this, not by subtracting the upper limit minus the lower limit, because that would make you think that the class width is 0.4 in this case. But that's not what we do. What we do is we subtract consecutive lower class limits. So that's this number and this number. If you subtract those, then you get the 0.5 that you should get. So what's the class width for the baby weight example above? Well, we've said this many times, right? But it's 0.5. Okay. When we're creating classes for a frequency distribution, we prefer to avoid confusion by ending one class right before the next one starts. So instead of writing things out like this, where this number and this number match, we prefer to write something like this, or maybe even something like this, so that the upper class limits and the lower class limits don't match up. And the reason for that is because if you draw it this way, right, if you make your frequency table this way, then it's confusing about if a baby happened to weigh exactly 2.5 kilograms, it would be confusing. Should you count them in the first class or should you count them in the second class, right? Since 2.5 shows up both places. Whereas when we draw it this way or this way, it's really clear, right? If the baby is exactly 2.5 kilograms, then they go in the second class, right? Anyway, but the class widths on all three of these examples would be 2.5 because we calculate the class width by subtracting consecutive lower class limits, 2.5 minus 2.0, 2.5 minus 2.0, right? 2.5 minus 2.0. Anyway, let's look at an example. So here we're given a histogram and we're being asked to basically reconstruct the frequency table that corresponds to it. First, we're asked a couple questions. What's the class width? What's the sample size? I'll let you pause the video and see if you can work that out. Here are my solutions. So class width here looks like 3, right? 4 minus 1 is 3. 7 minus 4 is 3. 10 minus 7 is 3. So the class width is 3. What's the sample size? Well, this is that thing again where we have to add up the numbers, right? Add up the bars. There were 2 individuals in this class, 9 individuals in this class, 4, 6, 7, and 8. And so we can go back over to the Desmos calculator and punch that in and see what we get, right? So 2 plus 9 plus 4 plus 6 plus 7 plus 8. Whoop. We'll try that again. 2 plus 9 plus 4 plus 6 plus 7 plus 8. 36. And you may remember this back from lecture 1.1, but the symbol for the sample size is little n. So we'll say n equals 36. Now, as far as reconstructing the frequency table, the first class goes from 1 to 4. Well, not quite to 4, right? To just under 4, because the second class starts at 4. We could say first class starts at 1, the second class starts at 4. That means that the first class needs to end somewhere before 4, right? Maybe we call that 3.9, or you could call it 3.999 or something like that. Anyway, similarly, the third class starts at 7, and then the next one at 10, and then 13, and then 16. Okay? And then we can go back and fill in all the upper class limits. We can say the first class starts at 4, it ends just before 7, so maybe at 6.9. And the third class goes maybe to 9.9, and the fourth class goes to 12.9, and so forth. Whoops, we'll say 18.9, so that if there were another class, it could start at 19. And then as far as the frequencies are concerned, well, we've already written those down, right? There were 2 individuals in this class, and then 9, 4, 6, 7, and 8. Okay, so again, if you have several values that your numerical variable can take on, then it's usually a good idea to group into classes, okay? But sometimes you need to and sometimes you don't. Let's practice creating histograms in Art of Stat. So number 4 here says the following data, which can be found in that Excel workbook, represent the number of available cars in a sample of 50 households. Use Art of Stat to create a frequency and relative frequency histogram for the data. Do not group into classes. Okay, draw the histogram below. Use it to recreate a frequency and relative frequency table. Okay, well, let's see if we can do all that. I'm just going to go ahead and show you how to do this. This is our first time doing it, so you don't have to pause the video and try this one out on your own unless you want to. But in Art of Stat, again, you're going to go to artofstat.com, click on Web Apps, and we're going to use Explore Quantitative Data. And we don't want to do an example from the textbook. We have our own to do. So let's grab the data from our Excel workbook. This is example 4. I don't really want to grab the title. I don't want to grab the variable name here. I just want to grab the data, although I'm not sure it really makes a difference. But I'm just going to hit on my keyboard. I'm going to hold down Control Shift and then the down arrow. Control Shift down will select all that data. Alternatively, you could click and drag. The only downside to clicking and dragging is if you happen to have a data set that had like thousands and thousands of values in it, it's going to take you a long time to select it all. Whereas if you just use Control Shift down, it'll select it all automatically. Anyway, from there you can Control C to copy, and then come back over to Art of Stat, and Control V to paste. Okay, now you'll notice it's making kind of a funny looking histogram. It's also making a box plot. We'll talk about box plots later. So let me just unclick that box so it's not cluttering up the page. But it's making a funny looking histogram because I said at the beginning of the lecture that a histogram should have no gaps between the bars, and yet this is showing gaps between each bar. And that's because so Art of Stat, for whatever reason, decided to have a bin width of 0.5. What Art of Stat calls the bin width is what we've been calling the class width. So it's saying the class width for these bars is going to be 0.5. But if we don't want to group into classes, then each observation is its own class. And so we don't want a bin width of 0.5, we want a bin width of 1. So I'll just drag this slider over to 1, and that gets rid of the gaps, right? So there's our picture, there's our histogram. It looks like there was, and it's nice, you can hover your cursor over these bars and it'll tell you what the frequencies are, which is really nice. So it looks like there were 4 households that had 0 cars, and there were 13 households that had 1 car. And you might look at this and you might say, well, how do you know if it's 1 or 2? Because you have both numbers on this bar. But remember that this class that I'm hovering over right here, it starts at 1 and it ends right before 2. So you could kind of think of it like this bar represents all of the households who have anywhere between 0 and 2 cars, but not including the 2, which is equivalent to just saying this bar represents all of the households that have 1 car, right? So this is the households with 0 cars. There were 4 of those. The households with 1 car, 13 of those. The households with 2 cars, there were 22 of those, and so forth, right? 7, 3, and 1. Okay, We were asked to draw this in the blank space on our notes, so let's do that. And, you know, because we're human, we're not the best at making pictures and stuff. Just do your best. And then as far as the number of households, on our histogram, the tallest bar over here was 22. So we need to go to at least 22. But I think I'm going to take my cues from what Art of Stat did, and I'm going to go by fives, right? 5, 10, 15, 20, and I'll just go all the way up to 25. Okay, and then we just draw our bars, right? So there were 4 households with 0 cars. There were 13 households with 1 car. And 1 household with 5 cars. And there was nothing bigger than that. So that's our histogram. We could give it a title. We could call it something like cars per household. Okay. And now, as far as frequency and relative frequency tables are concerned, I've tried to leave myself enough space on the right hand so that I could draw that in. So we'll say number of cars, relative frequency, and we had 0, 1, 2, 3, 4, and 5. The frequencies are easy to read from the bar chart. Again, you can just hover your cursor over the bars and read these off. So there were 4 households with 0 cars. There were 13 households with 1. And so I'm just writing these down on my chart as I go. Right? 7 households with 3 cars. 3 households with 4, and then 1 household with 5. As for the relative frequencies, now you could do this by hand. Let me fix this 13. You could do this by hand by dividing the frequencies by the sample size, which in this case we were told was 50. And that's actually kind of easy to do in your head, because if 4 out of 50 households had 0 cars, that's the same as 8 out of 100, right? 4 out of 50 is the same as 8 out of 100. You just multiply both numbers by 2. Well, 8 out of 100 I know is just going to be 0.08. So this should be 0.08. If I double 13, it's 26. And then if I divide that by 100, it's 0.26. This should be 0.44. I'll show you in a second how you can find this in the graph, in case the math is freaking you out. Like if you're not understanding what I'm saying mathematically. Because we should be able to display the percent here instead of displaying the counts. So if I click this little box, then it changes these percentages. And when I hover my cursor over the bars, now it's giving me the percentages, right? 8%, which is the same as 0.08. 26%, which is the same as 0.26, right? So these are the numbers that we wrote down just a second ago. Okay. So that'll do it there for number 4. Here's another example. It says, consider the following data set of the length in centimeters of 40 fish from Lake Kauai. Okay, so we've got a bunch of fish lengths. It says, construct a frequency and relative frequency histogram for the data. Start your first class at 12 and use a class width of 8. Draw the histogram below. Use it to recreate a frequency and relative frequency table. Okay. Well, now that you've been through the process already, I think you could probably pause the video and try this out for yourself. The only thing that you'll have to be careful of is this time we do want classes, right? And it says to start your first class at 12 and use a class width of 8. So go ahead and pause the video and see if you can figure out how to get Art of Stat to do that. I'm going to go ahead and give you my solutions now. So first of all, let's open up the data set so that we can copy. So example 4 was down here. Example 5 is in the next tab over. So I'm going to click on that tab. And then I can Control-Shift down, Control-C to copy, and back over to Art of Stat. Let me refresh the page. And again, I don't want an example from the textbook. I'm going to do my own and Control-V to paste. Okay, so it looks like here it's using a bin width of 5. I want a bin width of 8. So I can drag this over to 8, or I can click on this little box that says enter bin width and just enter it manually. I also noticed that they're starting their first class at 10, and we were told to start our first class at 12. So I'm going to click on this box that says select starting bin, and I'm going to change this to 12. Okay. We don't need to worry about the box plot just yet. So I'll unclick that box to hide it. And there you go, right there. That's the histogram that we were asked to draw. So let's go back to our notes and draw it. Now, one thing that I don't love about the way Art of Stat draws their histograms is that even though we started this first, we started our first bin at 12, it still marks a 10 on the x-axis and just marks the bar starting kind of offset from that. So mathematically, like, it makes sense what they're doing, but I would just prefer if they would move the labels and label this as a 12, right? And go from 12 to 20, 20 to 28, and so forth. You can do that yourself manually, right? You can change those numbers when you're drawing it. And that's what I would encourage you to do. So that's how I'm going to draw it. So I'm going to go 12. If I'm using a class width of 18, then the next class would start at 20. And when we're drawing histograms, we typically will only put the lower class limits. We don't put both the upper and lower class limits on the histogram. We only put the lower class limits. So 12, 20, and then plus 8 more is 28. Okay, and then plus 8 more is 36, and so forth. 76 plus 8 is 82. Okay. The tallest bar on my histogram went up to 14. So we could do that, by 5s like they did in Art of Stat, or we could go by 1s, whatever you prefer. 1, 2, 13, 14, 15. Okay, and that should be good. Okay, so our first group, the 12 to 20s, there were 2 of those. 20 to 28s, there were also 2. 60 to 68, there were 3. 68 to 76, there were 0. Okay, there were no fish in this class. And then 76 to 82, there was 1. Okay, and then as usual, right, we want to say this is the length in centimeters. This is the number of fish. Or if you want, you can call it the count or the frequency or whatever. And this is length of fish in Korea. Okay. We were also asked to recreate a frequency and relative frequency table. I have not left myself enough room to do that, so I'm not going to. You're welcome to try to squeeze it in over here somewhere if you want, but I'm happy to just leave it. We already kind of saw an example doing that. Okay, something that we can talk about with histograms that we couldn't really talk about with bar charts was the shape of the histogram. A bar chart does not have an inherent shape to it. And the reason for that is because in a bar chart or a bar graph, since a bar graph is used for categorical data, you can rearrange the bars in any order you want. With a histogram, and because you can rearrange the bars, you can change the shape of the bar chart to be basically whatever you want it to be. So it doesn't make sense to talk about the shape of a bar chart. There's no inherent shape to a bar chart. Histograms are a different story because the data that we're displaying in a histogram is numerical, and so it does have an implied order to it. And therefore, the histogram is always going to have, if you make a histogram for a particular data set, you cannot rearrange the bars to get the shape to change how you want. The shape is inherent to the data that it's describing. So anyway, so we can talk about the shape of a histogram. And this is actually going to be very important for us because the way that we treat skewed data, like this or like this, is different from the way that we treat symmetric data, like this or like this. So being able to identify the shape of a histogram is really important. So let's talk about these shapes a little bit before I almost moved on. But yeah, this first kind of histogram is called uniform. Right, so this is a uniform distribution right here, and that's because the bars are all a uniform height. In the real world, maybe they wouldn't all be exactly 20. Maybe it would be like 20, 21, 19, right? But they would all be close to the same height. We would call that a uniform distribution. It's symmetric because what symmetric means is if you fold the graph in half vertically, like along this line, for example, the two halves match up, right? Roughly. So it's a symmetric distribution. It's uniform. This one is another symmetric distribution. We would call it a bell-shaped distribution because it looks roughly like a bell. And again, symmetric because if you were to fold it in half, then the two halves match up. This distribution is called a skewed right distribution. At first glance, that might seem a little confusing because most of the data is over here on the left. And so you might think, well, why do we call it skewed right? The answer to that question is because this looks like a symmetric data set, right? It looks like a bell-shaped data set, except that the right side has been stretched out. Like if you imagine that this bell-shaped distribution over here was made out of like some kind of stretchy material, and you pulled on the right-hand side, then you would end up with this distribution down here, right? So we call it a skewed right distribution. It's been pulled to the right. And in a similar way, this distribution is called a skewed left distribution because it looks like we started with a bell-shaped distribution, but then yanked on the left-hand side. Okay, so it's skewed left. Okay. Now, a second ago, I said the shape of a histogram is inherent to the data set that you're using to make the histogram. There's a little caveat there, right? So the shape of a histogram is going to depend somewhat on the way that you construct your classes, if you're constructing classes for it, right? Too many classes will result in a histogram that's too sparse, right? Too spread out to give useful information. And too few classes will result in a histogram that's too bunched up to get a lot of useful information out of. So you kind of have to, this is a little bit more of an art than a science, but this is the histogram that we just constructed in Art of Stat. And this is just about right. Again, it's maybe a little bit more of an art than a science, but we want to avoid histograms that are really sparse and bunched up, okay? Also, where you choose to start the first class will have an effect on the height of all of the bars in the histogram. So again, this was our histogram that we drew in Art of Stat a second ago, where our first class started at 12. This one is a histogram with the same class width, but starting our first class at 10. And you'll see that the bars change heights a little bit, because we started at a different place. There really aren't any set in stone rules for how to set up your classes to get a good histogram, so you can just play around with it a little bit in Art of Stat until you get a nice looking picture. With that said, on a test or a quiz, I would probably tell you what class width I want you to use and what starting point I want you to use for your first class. So you won't have to worry about that on a test or a quiz. I think in the most part on homework assignments, it's the same thing. But if you're not told and you're just making a histogram you're just trying to determine what the classes should be, then my advice would be just get into Art of Stat and kind of play around a little bit until you get a nice looking histogram. Another thing I would point out is that while the histograms do all look kind of slightly differently from one another, they are all still roughly bell-shaped. I would call this a bell-shaped distribution. Okay, and that's what I mean when I say the shape of the distribution is kind of, or the shape of the histogram is inherent to the data that you're using, the data that you are trying to visualize with the histogram. So they're all roughly bell-shaped. Okay, so real quick, I just want to go through these. Example 6, it says, consider each data set below. In each case, decide whether a bar graph or a histogram would be more appropriate for the data. Decide whether to group into classes, and if so, where to start the first class and what the class width should be. Then create the graph and comment on the shape of the distribution as appropriate. Okay, and we're not given any background information as to what these data sets represent. But looking at part A, looking at the numbers there, first of all, I noticed that in terms of whether I should be making a bar graph or a histogram, I should be making a histogram on part A because this is numerical data. It's not categorical data, so I don't make a bar graph, I make a histogram. But second of all, deciding whether to group it into classes. Looking at this data, it looks like the smallest value is 0 and the largest value is 5. And there just aren't a ton of different values that the variable can take on, right? They're all whole numbers between 1 and 5. I would say we don't need to group into classes here. So we would make a histogram because the data are numerical, and we would not group into classes. Okay. And I think we've already done this, actually. I think this is exactly the same data set that we already looked at earlier, but just in case, we can open up the data set, select the data, Control C, and paste that here. Let me refresh. Control V. I don't want classes, so I'm going to make my bandwidth or bin width 1, and there we go. Right there's our histogram. Now, I'm not going to make you draw this in the notes, but we were asked to comment on the shape of the distribution, and I would say that this one is skewed right. I would say it's skewed to the right. So I guess this wasn't exactly the same data set that we looked at before, is it? I don't know, I can't remember. But it's definitely skewed to the right. Part B. Again, I've got numerical data here, so I'm going to make a histogram. This time it seems like I have some pretty low values, 22, going all the way up to some much higher values like 68. And so it seems like there are a lot of different values that this variable can take on. If I make each observation its own unique class, that's going to make a really not a great summary. So here I think we should group into classes. And of course, we weren't told what class width to use or anything like that. So I think we'll just have to play around with it in Art of Stat to kind of come up with a good looking histogram, and then we'll come back and we'll write down what our starting point was and what our class width was. Probably our starting point will be 22 because I think that's the smallest value in the data set. But anyway, let's head over to Art of Stat and play around. Let me erase these. Oh, come on. And go grab the data. Control Shift down, Control C, and Control V. Okay. Well, the default setting that Art of Stat is coming up with isn't bad, but I think that's a good looking histogram. It looks like it's using a bin width of 5, and it's starting its first class at 20. I'm not sure what the smallest value is, but look at this really nice feature. We can sort the values from smallest to largest. It'll take our data and put it smallest to largest. That's really, really nice, because now I can see for sure that the smallest value is 22. And so if I want, I can start at 22 instead of 20. Either way, so there's what we get if we start at 22. If we start at 20, we get that. As far as the shape of the distribution is concerned, I think either way, I would call this roughly bell-shaped. 22 doesn't look quite as bell-shaped as 20, right? 20 looks almost perfectly bell-shaped. But I would say in either case, I would call this a bell-shaped distribution. So here we're looking at a class width of 5 and a lower class limit of 20 for our first class. So let's go back to the notes and write that down. So we used a class width of 5 and a starting point of 20. And we got a bell-shaped. Oh, come on. This lag is killing me. Bell-shaped. Okay, last one, part C. Well, clearly we have some categorical data here. So histogram is out of the question. We have to make a bar graph. Okay, so don't forget the stuff that we talked about in the previous section, section 1.2, right? You make bar graphs for categorical data like this. Obviously, since it's a bar graph, there are not going to be any classes. So heading back over to Art of Stat, we have to use a different app, right? Because we're not dealing with numerical, or in other words, quantitative data. We're dealing with categorical data now. So we're going to use the Explore Categorical Data app. And let me select the data. And we have our own individual observations, which I will paste. And there you go. There's a beautiful looking bar graph. Doesn't make sense. It does not make sense to talk about the shape of the distribution. You can reorder the bars. For example, if I select Pareto chart, then it arranges the bars from tallest to shortest. So there's no inherent shape here, right? The shape's going to change. You can sort the bars however you want, right? We can put banana first, and then apple, then pear, mango, whatever order. And then the shape is going to change. So it doesn't make sense to talk about the shape in this particular case. So it doesn't make sense to talk about the shape. I'm not going to write that, but you can write it on your notes. That's all I have to say. This was a bit of a long one. Thanks for hanging in there, and I'll check in with you in the next lecture.